Hi guys, welcome to the fifth video in this unit on solution equilibrium. This is going to be based on 17.4 in your book, and now we're going to start talking about solubility equilibria. So the first three sections were on acid-base equilibrium. Now we're going to be focusing on solubility equilibrium, and again, this is 17.4 in your book. So before we actually get into what solubility equilibrium is, first you need to know your solubility rules. So all ionic compounds, or all salts that contain potassium nitrate, ammonium, and sodium are soluble. Now these aren't the only ones, but these are actually the only ones that AP requires you to know. So what AP says is if it's not potassium nitrate, ammonium, and sodium, that you assume that it's insoluble. The reason that you need to know these ionic compounds is because these ionic compounds are strong electrolytes and they dissociate into their ions. So there's no equilibrium that exists with strong electrolytes. The equilibrium that we're going to be looking at are those salts that do not dissolve completely. So they are weak electrolytes. They're insoluble in water. And so what we actually do is we classify these salts based on solubility. And solubility is the maximum amount of solute that you can dissolve in a specific amount of water. So what we're going to do is we're going to focus on the solubility product constant in this video. So let's consider that we have a saturated solution of barium sulfate that's in contact with solid barium sulfate. So what this means is we have barium sulfate that we've put into water. Now we know from the solubility rules that barium sulfate is insoluble. However, being insoluble does not mean that none of it dissolves in water. Okay, so knowing that something is insoluble in water simply means that it exists at equilibrium. So when we put barium sulfate into water, we have equilibrium. We have these double arrows. And so because we're at equilibrium, if we put barium sulfate into water, we put solid barium sulfate, we actually do form the barium and the sulfate ions. And this exists at equilibrium. So we can shift either way. So if we add more barium ions, it's going to shift to the left and it's going to precipitate out some of the solid. So insoluble compounds simply exist at dynamic equilibrium with their ions. So since barium sulfate is a pure solid, if we wanted to write the equilibrium expression for this, which would be KSP, solubility product, it depends only on the ions, because when you write an equilibrium expression, no matter what you're working with, you only include gases and aqueous solutions into the K expression. Now again, like I said, because we're looking at a solid dissolving in water, we use KSP. Okay? SP means solubility product. So KSP is equal to the concentration of barium ions times sulfate ions. Notice because the coefficients are 1, we just have 1s as the exponents and we don't even show them. So KSP is the equilibrium constant for the equilibrium between an ionic solid, typically insoluble, and its saturated aqueous solution. And KSP is called the solubility product constant. Now, the larger the KSP, so typically you see negative exponents. So you can say more positive, right? The less negative. So the larger the KSP, the more soluble it is in solution. The smaller the KSP, the less soluble it is. So if you're looking at 2 times 10 to the negative second and 2 times 10 to the negative 12th, your KSP of 2 times 10 to the negative second, that's bigger. That's going to be more soluble than the solute that is 2 times 10 to the negative 12. So in general, solubility product is equal to the product of the concentrations of the ions raised to their coefficients. So here we have aluminum carbonate. Okay, this is a solid. I thought I included it in here, but that's okay. So this is a solid. Ions are always aqueous, right? So this is aqueous, this is aqueous. So our KSP only shows gases or aqueous solutions. So we have the aluminum ion to the second power, the carbonate ion to the third power because of its coefficients. So it's going to be really important that you make sure when you write out the balanced equilibrium that you've actually balanced the reaction. So when we look at solubility versus KSP, solubility is the amount of substance that dissolves to form a saturated solution, right? It's the maximum amount that you can dissolve. This is usually expressed as grams of solid that will dissolve per liter of solution. So solubility is typically given as grams per liter. However, we are going to be working with molar solubility. Molar solubility is just moles of solute dissolved per liter of solution. So molar solubility is moles per liter. It's basically concentration. However, we can't actually have a concentration of a solid. So what we do is we call it molar solubility instead. How many moles of solid can be dissolved into a liter of solution? So solubility is actually used to find KSP, and KSP can be used to find the molar solubility. And we're going to be looking at different examples where we're actually solving for both. So with solubility and KSP, so if you're given the solubility of a compound in grams per liter, you can actually find the molar solubility simply by multiplying by the molar mass, right? Or dividing. It depends on which way you need to go. You multiply or you divide, just use factor label, use dimensional analysis, use the molar mass to get from grams per liter to moles per liter. And then we can actually use the molar solubility of the compound to find the molar concentration of the ions. All you do is you just use the formula of the solute. So, for example, if it is, calcium fluoride, CaF2, that means that for every 1 calcium fluoride, you have 1 calcium ion. For every 1 calcium fluoride formula unit, you have 2 fluorides. So you'd have to actually multiply by 2 to get the fluoride ion concentration. And we're going to look at that again. And then to go from concentration to KSP, we just use the solubility equilibrium. So here's just a quick example, and I know this looks like a lot of work, but we're going to talk through it. So the KSP, right, solubility product constant, this is the equilibrium constant, for calcium fluoride is 3.9 times 10 to the negative 11th. Now, KSPs can be found in Appendix D. So not only can you find the Ka and the Kb, you can also find KSP. So the KSP for calcium fluoride is 3.9 times 10 to the negative 11th at 25 degrees Celsius. Remember, equilibrium constants are always the same number as long as you're at the same temperature. So what is its molar solubility? So molar solubility, you are looking at the moles per liter of the solid. Okay, we want to know the molar solubility of solid calcium fluoride. So we followed the same format, the same steps that we've done with all equilibrium. First thing we need to do is write the equilibrium reaction. So we have calcium fluoride, which is solid. Right? This is typically insoluble based on solubility rules. What that means is it only partially dissociates, much like a weak base. It only partially dissociates into its ions. So it's at equilibrium with calcium 2 plus and 2 fluoride ions. So then we can write the KSP expression. KSP is equal to the concentration of the calcium ions times the concentration of fluoride ions squared. And that equals KSP, and KSP is 3.9 times 10 to the negative 11th. Now we can create a nice table. So we have initial change in equilibrium. So we are really solving for the initial concentration or the initial molar solubility of calcium fluoride. That's really what we're trying to find. Now, before you put that calcium fluoride into water, you don't have any of the ions. You have 0 molar of both of the ions. And then the change in concentration. So we're just going to use X's again. So we're going to take some of the calcium fluoride away as it dissociates. And then we get plus X for calcium and plus 2X for fluoride because there's a 2 in front. Now notice at the equilibrium, I put dashes through calcium fluoride because this doesn't actually go into our KSP. So if I cross this out, that's going to help me remember, hey, this doesn't actually get put into the KSP formula. And then so at equilibrium, calcium is X, fluoride is 2X. So then we simply plug these numbers in to KSP, and then we solve. So we get 3.9 times 10 to the negative 11th equals X times the quantity 2X squared. Now keep in mind, when this 2X is in parentheses, you have to square both of these. So the quantity 2X squared is going to actually be 4X squared. So 4X squared times X is 4X cubed. So you get 3.9 times 10 to the negative 11th equals 4X cubed. You solve for X, and X is 2.1 times 10 to the negative 4th. Now look back at the ice table. Okay? X is equal to the concentration of the calcium ions. But because it's 1 to 1, that's also the initial solubility of calcium fluoride. So molar solubility is going to be 2.1 times 10 to the negative 4th. Notice that it's a very, very small number. It's a very small number. Does not, we don't get very many moles that actually dissolve. And then if you actually wanted grams per liter, we could just rewrite this big M as moles over liters. And then you could multiply by the molar mass to give you grams per liter, which would just give you solubility. So now in your notes you have example 1. It's A, B, and C. What I want you to do is I want you to actually try these examples. It's okay if you're not sure what to do. Use this video and use 17.4 in your book or use the book online to work through these problems. Use KSP, use what you know in order to solve these, and then we're going to actually go through these in class.